The petrochemical sector in Saudi Arabia is expanding into becoming a fully integrated global petroleum and chemicals enterprise that can play a crucial role in diversifying the Saudi economy beyond oil and realizing the kingdom's 2030 vision. The domestic refining systems facility Petrochemicals producing for Saudi Arabia is strategically located, and it is the most extensive system in the Middle East. Saudi Arabia produces fuels and specialty chemicals in the top-ranking refining and chemical business. So, it has all the necessary ingredients for a large and efficient global footprint that potential partners will find very attractive. The country aims to integrate energy industries directly to achieve optimized value across the value chain. The global chemicals market represents about $2 trillion annually. Despite its abundant supply of hydrocarbons, Saudi Arabia has just a below 10% share of that market, so there is still room for growth. Vision 2030 aims to transform the downstream business from a nominally integrated domestic refining and distribution system to a global, integrated refining and chemicals business. The kingdom will meet the need for refined products, create integrated refining and chemicals mega-complexes, and develop a vibrant chemicals conversion sector. Producing chemicals, particularly sophisticated, high-value chemical products that may be used for optics and in the aerospace industry, for example, is one distinctive way to accomplish this goal. Natural gas and oil in the petrochemical industry provides a major opportunity to contain carbon within newly formed molecules. Consequently, value-added chemicals are provided from natural gas, and the release of carbon dioxide into the atmosphere is avoided. From an energy transition perspective, natural gas can provide near-term benefits when it replaces more highly polluting fuels. Hydrogen produced from natural gas using conventional technologies such as steam methane reforming, SMR, is a clean and promising energy carrier for power generation and transportation fuel. However, carbon from this process is converted into carbon dioxide and released into the atmosphere. Thus, carbon capture is an option that could provide a near-term solution for handling greenhouse gas emissions. The continuous withdrawal of carbon dioxide, the generation point, shifts the SMR and water-gas shift equilibrium to the right, thus increasing the overall hydrogen yield. In addition to hydrogen generation, syngas is essential in the current and future energy mix due to its applications in the production of the chemicals such as ammonia, urea, methanol, and ethanol, among others. Newly discovered natural gas field found in Saudi Arabia can be monetized through a variety of means, including the physical and chemical conversion of it to produce energy and chemicals. Saudi Arabia has the advantage of an abundant natural gas supply, which is exploitable at low cost, as a result of the shale gas revolution. Therefore, the use of natural gas and coal in the petrochemical industry provides a major opportunity to contain carbon within newly formed molecules. Consequently, value-added chemicals are provided from natural gas, and the release of CO2 into the atmosphere is avoided. The use of methane gas in the production of olefins and other chemicals has strong potential to be a game-changer in the chemical industry. Various studies are being tested to develop a cost-effective integrated methane-to-chemical process through syngas production. Once syngas is produced, it can be transformed into numerous intermediates and products. Examples of chemicals that can be transformed into products include methanol, ethylene, propylene, benzene, and liquid transportation fuels. The market for methanol is related to energy, which may result in a potential significant upside through the support by clean energy policies to lower emission fuel. China is the major driver of growth in the methanol space, with sustained demand due to China's increasingly methanol-to-olefin (MTO) projects. Methanol's price directions are partially influenced by Asia, which holds around 70% of total demand. Global demand for methanol is expected to grow at a 4% CAGR as per IHS and is stated to reach 97 MT by 2025. On the supply side, there is slight overcapacity. Capacities continue to increase in this segment as it is expected in the near term to have new projects beyond 2022. Polypropylene has become a substitute for a lot of minerals in the packaging industry. The global polypropylene market demand reached a volume of almost 80.8 MTPA in 2021. The demand is further expected to grow at a CAGR of 4.5% between 2022-2027 to reach a volume of almost 107.6 mtpa by 2027. Asia is the leading polypropylene market, accounting for nearly 62% of the total consumption of polypropylene, and China is known as the largest consumer of the product within the region. As crude oil is produced, it contains a certain amount of dissolved gas called associated gas. This gas contains hydrogen sulfide, carbon dioxide, nitrogen, methane, ethane, LPG, and natural gasoline gases. Before the 1980s, most of this natural gas in Saudi Arabia was flared, and the products were lost. However, with the commissioning of the master gas system in the early 1980s, this natural gas was gathered, sweetened, separated into finished products and sold. The remaining gas after the sweetening and NGL recovery processes is mostly methane. It is called sales gas, sold domestically as fuel. Gas processing plants receive associated sour gas well as non-associated gases. These gases are separated into three products: one, sales gas, predominantly methane, also called fuel gas; two, natural gas liquids, NGL contained ethane and NGL products; three, liquid sulfur, which is trucked to and sent sulfur globally. NGL fractionation centers separate the NGL into saleable products: propane, butane, and NG. Most of these products are sold locally while the balance is exported. Heavier hydrocarbons are the building blocks for the petrochemicals industry. Relative values or prices of these individual components, ethane, propane, butanes, pentanes, and gasoline fractions, C5+, are generally greater than the price of methane consumed as fuel. Saudi Arabia increased its daily gas processing capacity from 2 billion standard cubic feet per day, SCFD in 2000, to around 18 billion SCFD in 2022 to reach 20 billion SCFD by the end of 2023. The plan is to further expand gas business, including accelerating the development of the kingdom's unconventional gas resources to help meet the large and growing domestic demand for lower cost, lower carbon energy. Saudi Arabia gas processing facilities include Bahri, Fadhili, Harid, Hawiyah, Kursaniya, Midian, Shedgum, Sheba, Uthmaniyah, Wasat, and North Arabia. Natural gas is used for more than just power generation. It is also a major feedstock for the production of ammonia, which is used in fertilizer production, and for the production of blue hydrogen, which, potentially, will play an important future role in providing lower carbon energy. Saudi Arabia is among the world's leading producers of petrochemicals. Saudi Basic Industries Corporation, SABIC, now majority owned by Saudi Aramco, is the largest chemical company in Saudi Arabia and a global leader in the production of petrochemicals and plastics. Enabled by low feedstock costs and large-scale capacity expansion in recent decades, the petrochemical sector is the second pillar of the Saudi economy. Chemical exports, of which petrochemicals command the largest share, represent 35% of non-oil exports. However, potential for growth remains significant as a large share of Saudi domestic production consists of basic chemicals while more advanced specialty products are produced in other markets. Government investments in technology, production capacity, and gas exploration in line with Vision 2030 have supported broad growth in both feedstocks and downstream production. The petrochemical sector features indirectly throughout the Vision 2030, since it is one of the sectors that will help push up non-oil exports. More directly, the Saudi petrochemicals industry has been designated as one of the 7 national industries selected for concentrated support. Specifically, the vision emphasizes the need to build a unique logistical hub in which the enhancement of logistical services, state-of-the-art infrastructure, and streamlined trade exchanges are sought. The vision also emphasizes support for national companies, including petrochemicals, in helping them gain market share in both regional and international markets. The prominent role of petrochemicals in the non-oil economy means it has been identified in both the NTP and Vision 2030 as one of the sectors to lead the continued push for diversification away from fossil fuel reliance target to be 50% of GDP by 2030. Saudi petrochemical companies have their end consumers across the globe as the country is strategically located midway between both sets of major buyers US, Europe, as well as Asia-Pacific countries. Among Western economies, the trend appears to be veering towards closure of older plants in the US and Europe, while replacement capex is not being added quickly enough, thereby creating an opportunity for the Saudi petrochemical industry to expand market share in these economies. The kingdom is a key global player in both ethylene and ethylene derivatives, as most petrochemical firms use ethane as a key feedstock, which has a high production yield of ethylene. Saudi Arabia has a total production capacity of 17.5 mtpa of ethylene, which is about 9% of the total global capacity. Saudi Arabia could become the top supplier of hydrogen in the world. This may be of particular value to the kingdom in the carbon-constrained world that is characterized by a wave of net zero targets from governments and industries around the world. Moreover, hydrogen production speaks to the kingdom's existing expertise and supply chain capacities, such as its experience in industrial-scale production of hydrogen and chemicals, as well as the capture and storage of carbon dioxide. Its expertise and capacities can help underpin the Saudi vision for commercially viable production and export of hydrogen, which is based on hydrocarbon resources with the carbon capture, utilization, and storage of emissions. The development of a clean hydrogen industry, particularly the use of blue hydrogen, would also echo the kingdom's growing pursuit of a circular carbon economy, which is a framework for managing and reducing emissions through carbon reduction, reuse, recycle, and removal. Saudi Arabia is exploring ways to become the top supplier of hydrogen in the world and has clean hydrogen production targets of 2.9 million tons per year by 2030 and 4 million tons per year by 2035. The current focus is to gain a large market share in blue hydrogen, particularly in the form of blue ammonia, in the coming decade. The kingdom has the potential to produce 40 million tons of hydrogen per year if all of the methane is being converted to blue hydrogen. This is equivalent to 35% of the current total demand globally. Additionally, 80 million tons of carbon dioxide can be avoided. Hydrogen offers valuable advantages, as it avoids carbon dioxide and particle emission if produced from renewables, can be deployed at large scale, and can be made available everywhere. Hydrogen can improve the efficiency and flexibility of an energy system in two ways. First, the excess of electricity can be converted by electrolysis into hydrogen and be used in other sectors, such as transport, industry, and buildings, and second, it can be used as a carbon-free storage medium as a way to store energy for long periods. Three modes of storage can be considered for hydrogen, namely, as a compressed gas, as a liquid, or as solid absorbing metals. Some countries are not well positioned to generate energy with wind or solar power alone. For other countries, time may be needed to raise the necessary investment. As hydrogen has a high energy density and can be easily transported, it can redistribute energy effectively and flexibly. Hydrogen may be transported as a pressurized gas or as a cryogenic liquid. Gaseous hydrogen can be transported by highly pressurized pipelines or by tube trailers. Liquefied hydrogen can be transported in tankers. Hydrogen can help align global energy storage with changing energy demand. Its physical characteristics make it well suited to serve as an energy buffer and strategic reserve. By the year 2030, 250 to 300 terawatt-hour of surplus renewable electricity are expected to be stored in the form of hydrogen for use in other segments. Nowadays, battery electric vehicles are already used to reduce carbon dioxide emissions. However, fully decarbonizing transport will require deployment of fuel cell electric vehicles, having the same performance as gasoline vehicles. Fuel cell electric vehicles have several advantages. They actually zero emissions, have a good autonomy, 500 kilometers, and refuel quickly, from 3 to 5 minutes. Decarbonizing transport is particularly challenging because it represents a large share of total energy, and more than 30% of hydrogen's total carbon dioxide abatement potential is expected in this sector. Fossil fuels are the most used energy sources for industrial processes. Hydrogen can be an alternative when it is available as a byproduct of the chemical industry or when a specific industry needs an uninterruptible power supply. As hydrogen can be burned in hydrogen burners or be used in fuel cells, it offers a zero-emission alternative for heating. Nowadays, hydrogen is only used in industry for low-grade heat applications, process heating and drying, but is expected to be used with fuel cells in the future for not only low-grade, but also high-grade heat needs. Hydrogen could be used to convert captured carbon into usable chemicals, such as methanol, methane, formic acid, or urea. This technology is still in the research phase, and it is expected to be developed in the next 15 years. For example, in Iceland, geothermal carbon dioxide is used to generate electricity to produce hydrogen and ethanol by two thermophilic bacteria. By the year 2030, 10 to 15 million tons of chemicals may be produced from such renewable feedstock. The hydrogen supply chain consists of several echelons, including selection of energy source, hydrogen production, hydrogen transportation, hydrogen refueling, and hydrogen utilization subsystems. Of course, there is not a unique hydrogen supply chain. Even if there is clear evidence for the use of renewable sources, as already highlighted from an environmental viewpoint, the switch to a 100% renewable scheme can only be gradual, in order to satisfy both economic and environmental concerns as well as to take into account the availability of the energy source. Hydrogen can thus be produced using different energy sources, renewables or fossil fuels, and with different technologies, mainly steam methane reforming, SMR, electrolysis, and gasification, and distributed via pipelines or tube trailers. The main purpose is to store surplus electricity from fluctuating renewable sources by generating hydrogen via water electrolysis, with optional methane synthesis from carbon dioxide and hydrogen, via methanation process. The green hydrogen produced by renewable resources without pollution allows for the storage, transportation, and reuse of the energy when needed. The production of synthetic methane, synthetic natural gas results in lower total efficiency but could be advantageous in terms of feeding the produced energy carrier into the gas distribution grid. In contrast to the case of pure hydrogen, the injection of synthetic natural gas is not limited in amount. The synthetic natural gas or hydrogen can be used not only in electricity production, but also in other applications, such as mobility via fuel cells or natural gas vehicles. In 2018, about 115 million tons of hydrogen was used globally, of which 70 million tons was produced via dedicated production predominantly from natural gas, accounting for 71%, while coal was accounting for 27%. This production resulted in about 830 million tons of carbon dioxide emissions, around 2.2% of the global energy-related total. The main uses of this hydrogen were in refining, which was equivalent to 38 million. Additionally, ammonia industries used around 31 million tons, which have been used in particular for fertilizers production. Methanol usage accounts for 12 million tons, used mainly as a fuel additive and for plastics production. Hydrogen has spurred multiple waves of interest in the past without significant impact. Two factors make this time different. First, governments worldwide have rallied behind the target of net zero emissions by the middle of this century. Having a reasonable chance of limiting global temperature rise to 1.5 degrees Celsius, the goal laid out in the 2015 Paris Agreement, requires reaching net zero emissions by 2050. To do so, all sectors of the economy need to cut their emissions, including heavy industry and long-haul transport, where limited solutions exist. Hydrogen has emerged as a key option for reducing emissions in these sectors. Second, the plummeting costs of renewables and electrolyzers are improving the economic attractiveness of green hydrogen, that is, hydrogen produced through the electrolysis of water powered by renewable electricity. The increasing share of variable renewables, such as wind and photovoltaic, PV solar power, also creates demand for flexibility and storage, which hydrogen can help deliver. Green hydrogen can thus complement and extend the ongoing revolution in renewable electricity. As a result of these factors, hydrogen and hydrogen-based fuels are now projected to meet a sizable share of final energy demand in 2050, up from virtually nothing today. In all of these projections, current gray hydrogen production that is based on fossil fuels is completely phased out, and green hydrogen is the dominant production pathway, complemented by blue hydrogen, which is based on fossil fuels with carbon capture and storage, CCS. The hydrogen production market was valued at $130 billion in 2021 and is estimated to grow up to 9.2% per year through 2030. Additionally, global hydrogen demand is seen rising to 614 million metric tons a year by 2050, which would meet 12% of the total energy use. Hydrogen or hydrogen-based fuels, such as ammonia, are the leading option for decarbonization of sectors that cannot be easily electrified, including shipping and some industrial processes. Demand for hydrogen in power is not as high as in other sectors, but hydrogen could play an important role in providing flexible low-carbon electricity generation, helping us achieve a fully decarbonized low-cost power sector. There is more uncertainty in sectors such as heat, heavy road transport, and other industry where there are a number of competing decarbonization options, and the most cost-effective solution is dependent on how markets develop over the coming decades. Hydrogen demand for heat could range from zero in a scenario where heat is mostly electrified, to being the largest source of hydrogen demand if there is widespread use of hydrogen for heat. The kingdom began extracting natural gas to maximize the value of its oil extraction activities in the mid-1970s, with Aramco tasked by the Ministry of Energy, formerly the Ministry of Petroleum and Mineral Resources, to design and operate an integrated network to collect, process and transport natural gas in 1975. In the following years, comprehensive natural gas infrastructure was developed, forming a huge network of pipelines and 3 processing facilities, which are the Barry, Othmania and Shakam gas plants. To enhance the added value of the energy sector, 2 natural gas liquids processing plants were built in Jaima and Yanbu to supply feedstock to petrochemical projects. With these projects, the gas network and production sites were linked with demand centers throughout the kingdom to enhance the efficiency of the hydrocarbon chain and increase gas network's capacity to 3.5 billion standard cubic feet per day. In 2001, the Hawiah gas plant began operations, with a processing capacity of 1.4 billion standard cubic feet per day of non-associated gas. At that time, this single site enhanced the kingdom's supply of gas, providing electricity to support the kingdom's growing economy. The Harad gas plant was opened in 2003 to increase the gas network's capacity to 9.5 billion standard cubic feet per day. In late 2015, production began at the Wasat gas plant, one of the largest gas plants in the kingdom, with a total gas processing capacity of 2.6 billion standard cubic feet per day. In the end of 2019, production began at the Al Fadhili gas production plant, boosting total raw gas processing capacity to 2.5 billion standard cubic feet per day. In 2020, the development of the giant Jafurah field in the eastern province was officially announced, the largest unconventional non-associated gas field to be discovered in the kingdom. The kingdom's existing natural gas infrastructure is vast, and provides a quick, safe way to build experience using hydrogen in a wide range of applications. There are more than 10,000 kilometers of natural gas pipelines in the kingdom. The natural gas infrastructure provides an accelerator for the hydrogen economy. With an abundant supply of natural resources, there's an opportunity to convert gas molecules into hydrogen closest to where it's needed. And unlike its gray cousin, blue hydrogen sourced from natural gas includes carbon capture and permanent underground storage processes to prevent release of carbon dioxide into the atmosphere. This is an important step in the overall growth and adoption of hydrogen because natural gas has emerged as one of the cleanest forms of hydrocarbon energy sources. Natural gas-sourced hydrogen combined with carbon capture provides a massive opportunity to accelerate hydrogen adoption around the world in the near and mid-term, while ultimately transitioning to an increasing percentage of renewable or zero-emission feedstocks over the long term. Whilst hydrogen can be transported in existing pipelines, which have low operational costs and a proven track record, there are limitations with transporting hydrogen within the existing network. Liquid hydrogen is environmentally the safest option to transport hydrogen for very long distance to be exported. It does not require complex conversion and provides high-purity hydrogen. However, the liquefaction process requires high amounts of energy due to both pre-cooling and the liquefaction process itself. Liquid hydrogen must also be kept at -250 degrees Celsius, which requires new and specialist vessels. Therefore, ammonia is one of the favored mechanisms to transport hydrogen over long distances. Firstly, the cost of energy storage is cheaper than for either hydrogen or liquefied petroleum gas. Secondly, ammonia contains more hydrogen by volume than either pipelines or liquid hydrogen. Moreover, ammonia is already used across the world as fertilizer, meaning that it benefits from having a global transportation and storage infrastructure already in place. Lastly, due to its high use, it already has existing standards regulating its production, transport, and use. Compared to hydrogen, liquefied ammonia is far more convenient, practical, and cost-effective to transport, in terms of both the required temperature and pressure conditions. Once the blue ammonia reaches its destination, it can be converted back into blue hydrogen, or used directly as a fuel for gas turbines for cleaner power generation. The production and pilot shipment of 40 tons of blue ammonia by Saudi Aramco and SABIC utilizes and connects existing infrastructure and leverages the nearby industrial hubs and ports of Jubail in the kingdom's eastern province. The Saudi Arabian Fertilizer Company, ESAD FCO, an SABIC affiliate, operates 5 ammonia plants in Jubail, with a total capacity of about 3.6 million tons per year. SABIC also operates the world's largest carbon dioxide purification and liquefaction plant capable of purifying 500,000 tons of raw carbon dioxide for such uses as methanol and urea production. Natural gas is transported from the oil and gas fields to Jubail after being processed, where it is used as a feedstock to produce hydrogen by steam methane reforming, SMR, which then produces ammonia. Steam methane reforming is, to date, the most cost-effective way of making hydrogen. However, the process is energy and carbon intensive. In the case of the blue ammonia project, about 50 tons of carbon dioxide is captured, 30 tons of which is utilized in SABIC's Ibn Sina methanol plant. The remaining 20 tons are transported and injected into the Uthmaniyah oil field. The ammonia is then shipped to Japan to generate power at various production sites. The 50-kilowatt micro-gas turbine site in Koriyama and the 2-megawatt plant in Yokohama, where the ammonia is co-fired with natural gas, and a plant in Aoi where it is co-fired with coal. For the kingdom, the yet nascent hydrogen economy represents an opportunity to both diversify its commodity export portfolio and also gain an important foothold in it. Saudi Aramco has been working on carbon management, in the form of carbon capture, utilization, and storage, for decades. It began to inject carbon dioxide into one of the depleted sections of the Uthmaniyah oil field in July 2015 as part of an enhanced oil recovery pilot project. The enhanced oil recovery plant can receive 800,000 tons of piped carbon dioxide per year from Hawiah Natural Gas Processing Plant, located 85 kilometers away. Once injected into the reservoir, carbon dioxide becomes miscible under the right conditions, increasing the mobility of trapped oil in the porous media, enabling incremental oil gains. The process yields higher oil recoveries when injected into the reservoir and alternated with water, known as water alternating gas displacement. The water alternating gas displacement provides incremental recovery in the range of 5% to 10% of oil in place and may be as high as 20% in some cases. The cost of carbon capture, utilization, and storage has fallen by 50% in the past decade to $50 per metric ton of carbon dioxide in 2020, driven by the development and deployment of the technology. Saudi Arabia has a wealth of low-cost hydrocarbons and significant amounts of geologic space for carbon dioxide storage and nearby industrial hubs. These factors make it perfectly positioned to scale up carbon capture projects for further cost reductions and extend the lives of existing oil fields due to the increased reserves recovered using carbon dioxide injection. Saudi Arabia has nearly 500 oil and gas-bearing reservoirs across the kingdom, concentrated in the eastern province. One of the best chances to decarbonize challenging industries is hydrogen. For instance, due to practical technological constraints, some industrial sectors, such as steel, cement, or refineries are difficult to control directly with electricity, whereas others, such as marine, aviation, rail, or mining consume energy in quantities that are greater than what batteries can provide. These elements will promote hydrogen use regardless of the transportation sector and guarantee that clean hydrogen is easily accessible. We anticipate a sharp rise in the number of hydrogen-powered vehicles on the road over the upcoming years. Although the focus has been on passenger cars, which will also contribute to the consumption of hydrogen, commercial vehicles will eventually account for almost 95% of demand. Up to 15,000 medium and heavy-duty trucks powered by hydrogen could be in use by switching a segment of the natural gas to hydrogen. Together, they would need up to 170 along-the-way hydrogen refueling stations and use 2,000 tons of hydrogen annually. Reducing GHG emissions from the transport sector is a challenging area. One of the strategies for reducing carbon emissions is to expand public transportation and railway networks to connect major cities and ports. The Kingdom focuses on the circular carbon economy framework to realize its climate goals. The Saudi 2021 nationally determined contribution covers the following actions: energy efficiency. This includes maximizing the efficiency of home appliances and air conditioning units, feedstock utilization, improving the fuel economy of transportation fleets, phasing out inefficient and used light-duty vehicles, implementing aerodynamic regulations for heavy-duty vehicles, and improving thermal efficiency. Brine production or disposal and a vast carbon footprint resulting from energy usage are two major negative environmental implications of seawater desalination. Sequential carbon dioxide mineralization provides a possible solution to both problems. Wastewater or brine solution could be used as a liquid agent in the carbonation reaction. Oil field brine is another significant waste from oil and gas production, which is mainly disposed of. Aqueous sources such as seawater, subsurface brine, and industrial effluents are rich in calcium and magnesium, which can potentially be applied for carbon dioxide mineralization. In this process, carbon dioxide is transformed into carbonate precipitates and permanently stored as value-added products. 5,000 tons per day of carbon dioxide can be avoided from being emitted to atmosphere and instead injected to oil and gas fields, which have a 25 gigatons of carbon dioxide storage capacity in multiple giant storage formations. To produce 1 ton of sodium hydroxide, the chloralkali process needs 2.5 megawatts of electricity. With seawater serving as the source of both diluent and solubilized carbon dioxide, the energy requirement for direct carbon dioxide mineralization using sodium hydroxide as an addition to be around 4.5 kilowatt per ton of carbon dioxide, excluding water processing. With an energy intensity of 1.26 megawatt per ton of carbon dioxide, mineralization-based carbon dioxide management would cost, at the very least, $90 for every ton of carbon dioxide turned into solid carbonates utilizing divalent cations generated from seawater. An energy intensity of 1.5 megawatt per ton of carbon dioxide is estimated for amine-based carbon dioxide capture. Heat duty for amine regeneration is 1.3 megawatt, and for pressurizing the recovered carbon dioxide stream from atmospheric pressure to a pipeline specification at 14 megapascal. This estimate takes into account an inlet stream with 3% carbon dioxide, which corresponds to the flue gas emitted from a natural gas-fired power plant. As the percentage of carbon dioxide in the inflow stream rises to about 12% for a coal-fired power plant, this energy intensity falls to 0.8 megawatt per ton carbon dioxide, then stays constant after that. While the Kingdom's eastern region, with its great apparatus of oil and gas production, refining, and chemical industries, has much of the infrastructure in place to support the development of a blue hydrogen industry, including access to deep saline aquifers for carbon dioxide storage. The western region enjoys very strong solar and wind resources to produce low-cost electricity for green hydrogen production. The NEOM project, in the northwest, is already the site of what is planned to be one of the largest green ammonia production plants in the world. Its hydrogen will be used to produce ammonia intended largely for export. These unique regional advantages may allow the kingdom to pursue a broad hydrogen strategy that encompasses both green and blue hydrogen. Saudi Arabia's vast renewable energy potential and natural gas reserves will support it in producing some of the cheapest green and blue hydrogen globally. The kingdom has announced plans to install almost 58 gigawatt of renewable energy by 2030. Renewables-based hydrogen is a key focus of technological and economic advancement of NEOM. NEOM features a $5 billion green hydrogen project that is a joint venture between NEOM, Aqua Power, and Air Products. Expected on stream in 2025, the project's 4 gigawatt renewable capacity would make it the world's largest renewable hydrogen to ammonia facility in the world, producing 1.2 million tons per year of green ammonia yearly. Ports can play a crucial role in the production and distribution of green hydrogen. They are important nodes given existing and future local demand for hydrogen, the emerging offshore parks, and as junctions of transport nodes, some of which could shift to hydrogen or related fuels, for example, vessels, barges, trucks. Additionally, the infrastructure and handling capabilities of seaports make them prime locations for the storage and distribution of hydrogen. Seaports can serve as hubs for the export of green hydrogen to other countries, helping to drive the global transition to clean energy. Royal Commission of Jubail on the Arabian Gulf and Yanbu on the Red Sea coast are developing dedicated hydrogen pipeline networks within their industrial cities. The first network was commissioned in Yanbu Industrial City earlier this year. Industrial clusters in cities like Jubail and Yanbu are favorable locations for hydrogen hubs for several reasons. First, they can fully integrate industrial gas hubs centered on producing hydrogen via steam methane reforming with an associated pipeline network linking these hubs to industrial end users. Second, waste from one application, such as carbon dioxide from hydrogen production with carbon capture and storage or excess heat from steel production, can be used as an input to another application. Third, they provide infrastructure synergies such that heavy industries, particularly chemicals, fertilizer, and refineries, can interface with shipping, freight transport, pipelines, and renewables. With 13% of global trade moving through Oxagon, which is strategically placed in NEOM northwest Saudi Arabia, it has first-rate local, regional, and global connectivity. By combining an automated port with a smart supply chain network, Oxagon is being developed as the future of innovative and clean industries and as a center of innovation. It offers intelligent freight loading that maximizes throughput. Warehouses are directly adjacent to the port, providing access to the rail and road networks. Frontrunner cities are proactive in climate protection. In recent decades, cities have risen to become a new power in battling climate change, with more than 1,000 cities worldwide making net zero pledges as of 2021. In the emergent hydrogen economy landscape, a few early mover cities are actively developing and adopting hydrogen fuel for diverse purposes. For example, the Kitakyushu Hydrogen Town in Japan was launched as a demonstration project included in smart community initiatives. In Fukushima, the local goals of hydrogen adoption to build a society powered by 100% renewables and hydrogen energy. In addition, some pioneering cities in Europe expect the introduction of hydrogen fuel to help mitigate local air pollution and support economic growth. Some frontrunner cities in China are actively introducing local hydrogen strategies to enable technological innovations and adoption. Cities are regarded as the loci of knowledge production and technological innovation. They are where actors congregate and where capital and technical resources are concentrated. The innovative capacity of cities is positively related to their size, and innovation cycles are running at an accelerating rate to maintain sustainable growth. In addition, the creative capacity of cities is improved when activities are deeply embedded in intercity innovation networks, where inventor interactions can be enhanced. Importantly, policy effort is needed to navigate cities' innovation potential toward the desired directions. In an emergent landscape in which hydrogen is being adopted into energy systems, investigating the drivers, opportunities, barriers, and impacts of city-level hydrogen policies will provide timely new insights into cities' role in incubating technological innovations and will contribute toward accelerated hydrogen adoption. In the coming decades, industrial clusters, such as petrochemical hubs, will decarbonize gradually via: first, the reduction of fossil fuel-based refineries; second, the electrification of processes; third, where electrification is technically impractical or economically burdensome, large petrochemical units, like crackers, will be fueled by hydrogen rather than natural gas. Saudi Arabia's National Renewable Energy Program aims to achieve 58.7 gigawatt of renewable energy capacity by 2030. The Sudair solar voltaic power plant will be the largest solar power plant globally and should result in reducing carbon emissions by 2.9 million tons annually. The kingdom has the potential to produce 3.5 million tons of hydrogen per year if all of the renewables are being dedicated for green hydrogen production. The current focus is to gain a large market share in blue hydrogen, particularly in the form of blue ammonia in the coming decade, and expected to supply 2 to 4 million tons of blue hydrogen by 2030. Additional green hydrogen is expected to follow, adapting some of the existing and future renewable projects. The manufacturing processes that depend on the physical and chemical characteristics of molecular fuels for effective operation are the strongest application cases for hydrogen. Hydrogen can make it possible to move away from fossil fuels in many of these applications. Second, hydrogen would be sufficient to transition to renewable hydrogen for steel production, then for cement manufacture to use renewable hydrogen for heat. Finally, hydrogen could be used for the production of aluminum and glass. Large-scale local supply chains are probably where hydrogen will be most competitive. Dedicated pipeline networks with a variety of wind and solar-powered electrolyzers and a sizable geological storage facility to smooth and buffer supplies might meet the needs of clusters of industrial clients. In Saudi Arabia, our estimate predicts that supplied green hydrogen would cost about $2/kg in 2030 and $1/kg in 2050, making it competitive with existing natural gas.